Have you ever just wondered how physicists manage to solve these ridiculously hard problems? Well, I'll let you in on a little secret. It's not about being a super genius or memorizing a bunch of crazy equations. Nope. It's a special way of thinking, a mental toolkit for looking at the world. And today, we're going to crack that toolkit wide open.
So, to kick things off, let's try a classic physics-style puzzle. How much does all the water on planet Earth weigh? And I mean all of it. Every ocean, every sea, every single lake. It sounds impossible, right? I mean, you can't exactly pop the planet on a bathroom scale. So, where do you even start?
And here's the thing. This is the big secret right here. For a question this massive, the exact number, the final answer, it's not really the point. The real magic, the real genius, is in the method. It's about taking a completely impossible question and figuring out how to wrestle it into a reasonable answer using just the tools you've got in your own head.
All right, let's pull out our first tool. This is a big one. It's the art of the educated guess, a super powerful technique for estimating, well, just about anything you can possibly imagine.
This whole idea is called a Fermi problem, and it's named after the physicist Enrico Fermi. This guy was an absolute master at answering huge, epic questions with what he called back-of-the-envelope calculations. Basically, just breaking a giant problem down into smaller, simpler pieces that you can actually take a decent guess at. And the method, it's so simple, it's beautiful. Step 1, you just identify the key ingredients you're going to need to get to your answer, things you can make a reasonable guess about. Then, step 2, you figure out how all those little ingredients fit together to give you the final number you're looking for. And that's it. Okay, so let's get back to our water problem. To figure out the mass of all that water, we really need its volume and its density. Now, the density of water is pretty easy. We know that one. The real trick is estimating the total volume of all the oceans on Earth. So what pieces do we need to guess?
First up, what percentage of the Earth is covered by oceans? You probably know this one or can get close. A good simple guess is about 3/4 or 75%. Boom. That's our first ingredient.
Next, how big is the Earth? We need its radius. Now, you don't need to know the exact number down to the last meter. Remember, this is an estimate. A good round number that's easy to work with is about 6,000 kilometers. Okay, ingredient number 2 is locked in. And finally, how deep are the oceans? Ooh, this is a tough one, right? Some parts are crazy deep, some are shallow. But we just need an average. What feels about right? A kilometer? Maybe 2? Let's be conservative and go with 1 kilometer for our average depth. That's our third and final ingredient. Now, check this out. This is the amazing part. When you take our 3 simple guesses, 75% coverage, a 6,000 kilometer radius, and a 1 kilometer average depth, and you crunch the numbers, you get an answer that's somewhere around 10 to the power of 20 kilograms. And get this, that is incredibly close to the actual scientific value. We got there with just 3 educated guesses. Now that is the power of estimation.
But hold on, how do we even know our formulas make sense in the first place? Well, that brings us to the second tool in the toolkit. This is a way to check your work using the fundamental grammar of reality itself. It's called dimensional analysis.
It sounds kind of fancy, but the idea is actually super simple. Pretty much everything in mechanics can be described using just 3 fundamental dimensions: mass, which we'll call m, length, L, and time, t. So, for example, velocity is just a length you travel over a certain time, right? So its dimension is L divided by t. Everything is built from these basic blocks. The absolute best way to think about this is like grammar. An equation has to be dimensionally consistent. The units on one side of the equal sign have to match the units on the other. You can't have an equation that says, kilograms equal meters. That's nonsense. It's like trying to write a sentence where a verb equals a noun. It just doesn't work. This tool lets us check the grammar of our physics to make sure it's not talking nonsense. So let's try another problem with this new tool. Imagine a pendulum. How long does it take for it to complete one full swing, back and forth? That's called its period. Now, what could possibly affect it? The weight of the little ball at the end? The angle you release it from? The length of the string? A physicist looks at this and immediately starts to simplify. The mass of the bob at the end probably doesn't matter. We know from Galileo that things fall at the same rate no matter how heavy they are. So the only things that seem truly important here are the length of the string, which has the dimension of, well, length, or L, and the acceleration of gravity, g, which is pulling it down. Gravity has dimensions of length divided by time squared, or L divided by T squared. And it's so brilliant. We want an answer that has the dimension of time T. So how can we possibly combine our two ingredients, length L and gravity L/T squared, to get time? Well, think about it. If you divide length by gravity, the L dimensions on the top and bottom cancel out, and you're left with T squared. So to get just T, what do? You take the square root. The only simple combination that gives us a unit of time is the square root of L divided by G. Just like that, without doing any hard math, we figured out the basic shape of the equation for a pendulum's period. So these tools, they can feel like fun little mental games, right? But what happens when this kind of fundamental first principles thinking is ignored? Well, sometimes the consequences can be absolutely catastrophic. On January 28, 1986, the Space Shuttle Challenger tragically broke apart just 73 seconds after liftoff, and all 7 crew members were lost. The investigation that followed uncovered a deep, deep failure in exactly this kind of physical reasoning.
The legendary physicist Richard Feynman was on the investigation commission, and in his report, he wrote this absolutely devastating line. What he found was that officials had convinced themselves they understood the risks, but their confidence, it wasn't built on a solid foundation of understanding.
And here's the crucial point. The engineers had a formula to predict how certain parts of the rocket would wear down over time. But this formula wasn't based on a real deep understanding of the physics, the why behind it all. It was just based on connecting the dots between old data points. So they knew what had happened in the past, but they didn't really know why it happened. And because of that fatal flaw, they couldn't predict a catastrophic failure under new conditions, like the record-breaking cold temperatures on launch day. That's a really heavy but absolutely vital lesson. This way of thinking isn't just some academic exercise. It has real-world importance. And the good news is, now this toolkit, it belongs to you. So let's recap our 2 powerful new tools. First, we've got estimation, using Fermi problems. This lets you break down any giant, scary question into smaller, bite-sized pieces you can actually guess. And second, we have dimensional analysis, the ultimate grammar check for reality that makes sure your logic and your equations are actually sound. And why does this matter to you? Because these tools are not just for calculating the mass of the ocean or the swing of a pendulum. This is a framework for thinking critically about anything. They teach you to simplify, to check your own assumptions, and to build an argument from the ground up. You can use this to analyze a business plan, a news article, or any complex problem that life throws at you.
So, I'll leave you with this question, this challenge. Look at the world around you with your new toolkit. How many piano tuners are there in Chicago? How many blades of grass are on a football field? What seemingly impossible problem will you try to solve first? Thanks for joining me.